Good morning. So today we are going to try to tie together sort of all of the different concepts that we've discussed along the way, from electrostatics, electrodynamics, alternating current, magnetic fields, induction, all those things we're going to tie together uh, when we introduce Maxwell's equations, which is a formalism that really set the foundation for how modern day uh, understanding of electricity and magnetism is formed. Um, so I want you to think a little bit about the four fundamental equations that we've learned this semester. And I've written them up here. There's Gauss's law. So try to envision in your head what that equation looked like. We had Gauss's law for magnetism, which we didn't use a whole lot, but we introduced it. And then we had Ampere's law and Faraday's law once we started talking about currents and magnetic fields. All of these equations had some integration, had some integral term. They had some integration over an area in the case of Gauss's law, or around a circuit in the case of Ampere's and Faraday's law. They were related to some sort of change or some sort of quantity, like charge or current. Today we're going to try to connect all four of those laws together. So that's where we're going. We will have to start by correcting Ampere's law. This was something that Maxwell did. And when we add this little correction, then we can start to see a similarity between Ampere's and Faraday's law that will point towards how we're going to combine all of these four main laws. And when we do that, what will pop out is electromagnetic waves. So light, other forms of electromagnetic radiation, so radio waves, heat, things like that. And then we'll spend the rest of the rest of the chapter, most of which we will not get to today, but after a break, we will discuss things like the speed of light, how light propagates as plane waves, some of the properties of those waves, and general properties of electromagnetic spectrum. So that's where we're headed. And where we're going to start is by going back to Ampere's law, which told us that if we had some sort of current, we could draw a loop, we'd call it like an Amperian circuit, around that wire and figure out the magnetic field at that distance along that loop. And the magnetic field integrated along that loop was equal to mu naught times the enclosed current. So that's easy enough to do when we have a wire carrying a current. But what if we consider a wire coming into a capacitor? So here's one plate at the capacitor. Here's the other. And of course, there's nothing between them, or at least no conductor between them. But we can send a current onto this capacitor to charge it up. So if we draw our Amperian loop around this wire, as we send current in, we imagine that there'd be some magnetic field produced around this. And we could work out what that is pretty easily. But when we talk about the current that passes through that loop, it's natural to think about like this planar surface that connects all the points in the perimeter of this loop. But what if we instead took a bulging surface that went like this, that passed through the center of the capacitor? Is there current now passing through that surface? There certainly is no wire piercing the surface where charges can flow. And in fact, there are no charges passing through the surface. If you were to somehow observe the charges that pass through the surface, you wouldn't see any here. But you would when you did this surface. But both of those surfaces are bounded by the same little Amperian loop. So in one case, we might expect there'd be no magnetic field around this loop because there's no current passing through the surface. But in the other case, we would expect there is a magnetic field around this loop because there's a current passing through. And this is a paradox that Maxwell set out to resolve. So what we do have in the middle of the loop, or in the middle of the capacitor, is an electric field. Okay, and if we want to work out the relationship between that electric field and the charge that flows onto the capacitor, we know for a capacitor that Q equals Vc. It's just the relationship between charge and voltage on a capacitor. And if it's a parallel plate capacitor, the voltage between the plates is E times D, where E is the electric field between the plates, which is a constant. D is the separation. And so we know when we do a line integral along an electric field, we get a change in voltage. So that voltage can be written as E times D. And the capacitance of a parallel plate capacitor we could write as epsilon A over D, where A was the area of the plates, D was their separation, and remember epsilon was the permittivity of whatever material is in the middle. So if it's vacuum, if it's empty, it would be epsilon naught. Well, we have a D in the denominator over here and a D in the numerator over there, so those cancel, and we get epsilon AE. And this area of the plates times the electric field coming off of the plates. We have a name for an area times an electric field, or an area times a field. That's a flux. Right? We've dealt with magnetic flux quite a bit. We dealt with electric flux a little bit. And so this is the electric flux, the area of the plates times the electric field on those plates. So we can write that as phi sub E. And now what we're interested in is finding something equivalent to a current that passes through a wire, but for the space between the plates of a capacitor. So this was the charge on the capacitor, and the current flowing onto the capacitor is just the rate at which that is changing. Right? Current is just dq dt, the rate of flow of charge. So if the charge on the capacitor is related to the electric flux inside the capacitor, then the time rate of change of the charge is equal to the time rate of change of the electric flux. Right? And we have this constant epsilon that gets included. And that's just the current. So the current flowing onto the capacitor must equal epsilon times the time rate of change of the electric flux. So as charge flows into the capacitor, the electric field builds up, and therefore the electric field is changing. And so you can't have current flowing onto the capacitor without having a changing electric field inside of it. So these things are equivalent, and that gives us a hint how we can fix Ampere's law. Ampere's law has a current on the right side. The current passing through our Amperian circuit is what appears on the right side, and we're going to call that the conduction current. It's the current that is conducted, where charges are flowing in a wire. And we're going to add to that this term up here, which Maxwell called the displacement current. And it was a term that he derived and added on to Ampere's law, so that we have not only the current flowing in wires, but the equivalent effect inside a capacitor due to changing flux. And in our example, depending on how we drew the surface, we either have a conduction current or we have a displacement current, but they're equal to each other, so we could use either one. And in general, you could have some of both, so we include both. So this doesn't change how we use Ampere's law. If we just have a wire and we want to find the magnetic field around it, then we don't have to include this term, because we don't have electric flux. We just have current. But if we have a capacitor or some other region of space where there's no charges flowing through the region, but there's a changing electric field, then we use this term. So that was one thing that Maxwell did when he looked at these equations that had been derived by other people. He looked at Ampere's law and he fixed it. He made it, he resolved this paradox. The other thing he did is he recognized that around a loop, if you integrate the electric field, you get the EMF around that loop. And that's something that we've introduced and we've used a little bit. But using that relationship, he could rewrite Faraday's law in a way that makes Faraday and Ampere's law symmetric. We'll see in a second. And then he recognized that Gauss's law for electricity and magnetism had a symmetry that could all be combined into a cohesive set of 4 equations that are now known as Maxwell's laws. He didn't invent or derive any of these laws himself. He just fixed them and combined them and recognized that they were related. And we can use these 4 laws basically to derive anything involving electricity or magnetism. Okay, so he published a paper in 1865, the Treatise on Electricity and Magnetism, that forms the modern foundation for our understanding in this field. And this was considered one of the greatest leaps forward in physics and really all of science. If we look at these laws, there are some things that we can see right away that are similar, like Gauss's law for electricity and Gauss's law for magnetism. The left sides look very similar. We just replace an E with a B. The right sides look pretty different. Ampere's law doesn't look much like Faraday's law at all, but if we include Maxwell's corrections, here's Maxwell's corrections to Ampere's law, and here's his correction to Faraday's law, where we write that EMF as the integral around a loop of E dot dl. Now we can see the left sides look very similar. We just replace the E with B and vice versa. And the right sides look very similar. We're just replacing the magnetic flux with the electric flux. And then we've got this pesky little difference that there's a current here and there's a charge there, where there is no current here and no charge there. And really the reason for that difference comes down to the fact that electric charges exist, but magnetic charges don't. We don't have individual magnetic monopoles. You don't have just a north pole of a magnet on its own. It always comes combined with the south pole. So we say there are no free magnetic charges. If there were, these are what the equations would look like. And now we see they're almost term for term symmetric. Right? Q magnetic would be like the amount of magnetic charge, the amount of north poles you have. But in reality, no one's ever observed an independent north pole of a magnet or an independent south pole. So we take this to be 0. And if there's no magnetic charge, then there also can't be a magnetic current. You can't have a flow of magnetic charges if there's no charges. So this term, I magnetic, becomes 0. And we go back to this form right here. So this is the form of Maxwell's equations that we use, but we can see how related they are when we imagine what they would look like if there were magnetic charges. And so those laws are considered very beautiful. You'll see these sort of in pop culture quite a bit. You can buy t-shirts with Maxwell's equations on it. Some of the most common ones said, and God said, and then lists the 4 equations, and then there was light. And the reason is, we can use these equations to derive the laws of, well, the wave equation, which gives us propagation of light. Okay, we're going to do that today. Apparently some people have these tattooed on their arms, carved on a pumpkin. They come in different forms. So we're working with a form that looks sort of like this over here, where we have this integral on the left. But you'll also see it in what's called differential form, where where we basically take the derivative of both sides, and you have these things called del operators. So this looks a little different. It represents the same thing in just a slightly different form. You'll probably work more with this form when you get to your upper division classes. If you do upper division physics or maybe electrical engineering, you'll encounter these again. But I just wanted to point out, because you'll see these. In fact, if you walk down the hall, they're stenciled on the wall just around the corner on the 2nd floor. But you might not recognize them initially because they're going to be in this differential form that's over here. Okay, so first let's try to understand conceptually how these rules of electricity and magnetism that Maxwell organized gives rise to electromagnetic waves. And once we do that conceptually, we will derive it mathematically. So we know if there's an electric field that changes, which was Maxwell's correction to Ampere's law, that tells us that there's going to be a magnetic field circulating around. Okay, just as if there's a current, there's going to be a magnetic field circulating around it. Now, if the electric field's rate of change itself changes, okay, so there's some maybe acceleration of the current flowing onto a capacitor, then the magnetic field produced, not only is there a magnetic field produced, but its amplitude changes. And Faraday's law tells us that a magnetic field passing through a circuit produces an electric field around that circuit. It produces an EMF, which is basically an electric field circulating around that circuit. And if the magnetic field is changing, then the electric field amplitude is changing. And if the electric field amplitude is changing, that's going to change the magnetic field. And if the magnetic field changes, that's going to change the electric field. And if the electric field changes, that's going to change the magnetic field. And that's what propagates as a wave that we call light, or radio waves, or microwaves, or gamma rays, or X-rays. Any form of electromagnetic radiation is driven by these interactions. Okay, so this was first experimentally detected by Heinrich Hertz in a famous experiment where he took basically a battery and connected it to what's called a spark gap. This is essentially a large capacitor that can store charge from the battery, and then a small airspace between the two conductors where you could get a little arcing, a little spark. And then over here, there's a metal ring with a slight break in it. So there's a gap there called a spark gap. And when he threw a switch here that allowed these capacitors to charge up and then a spark to form, he observed a spark over here in the gap. And the reason is that little spark was a current of electric charges that produced a changing magnetic field, that produced a changing electric field, that propagated as a wave. This basically was an antenna. The passing magnetic field through that antenna produced an electric field around here that then was strong enough to produce a spark in the gap. So this is, you can think about it as wireless power transmission on a very small scale. You can think about it as electromagnetic communication. A signal, in this case a single bit, a spark, was produced here and detected over here through wireless transmission. And so this gives rise to what? Cell phones, satellite communication, radio, light, like all that stuff that we take for granted that's part of like modern society was first sort of proven in this Hertz experiment. And so Heinrich Hertz was asked what he thought the ramifications of his discovery were. Do you know what he replied? He was a visionary. He didn't think it meant anything. No, he was wrong. Okay, so let's try to work through the derivation using Maxwell's equations of this propagation of a wave as an electromagnetic field. So let's imagine that we've got an electric field that varies in the x direction and is polarized along the y direction. So the electric field points along y, and so here's my x-axis and my y-axis. So the electric field points along y, but it varies along x. So we've got a larger electric field, maybe further out on the x-axis. So I've drawn the electric field at 2 points in space along x with slightly different lengths. And what I want to do is I want to consider a loop that has a height that I'll call L and a width that I'll call dx. Okay, so it's a very narrow loop. And I'm going to be able to use this loop to calculate E dot dl around the loop. And I'm going to consider all of my calculations around a counterclockwise loop. Okay, so because the electric field is varying along x, and because I only care about the electric field on the left and the right side of this loop, which is very narrow, I can write any arbitrary function of x as a Taylor series expanded around some point that I care about. And to good approximation, if I'm close enough to that point, I can consider only the first order term in the Taylor series. So if I expand E of x and want to evaluate it at a neighboring point, E of x plus dx, that's going to equal the value at E of x plus whatever the slope of the electric field with respect to x is, times the distance away I am from x. Okay, so that's just the first order term in a Taylor series expansion of E of x. And this is a tool that we'll use to simplify our calculations. Okay, so what I want to do is apply Faraday's law, which says that the integral of E dot dl, that's the EMF around the loop, is equal to minus the change in magnetic flux through the loop. So I'm going to have some magnetic field pointing through the loop that will be in the z direction. And if E dot dl is not 0 around the loop, which by the way it's not if the electric field is not constant, because as I've drawn it, it's bigger on the right than it is on the left. And the electric field pointing along y is not going to have any contributions to E dot dl on the top or the bottom of this loop. So when I evaluate E dot dl on the left side, what I've got is the electric field over here at E of x plus dx, that's this, and it's pointing in the direction that I'm going around the loop, and I go for a distance L. So E dot dl is just this product for the right-hand side of the loop. It's 0 on the top because my electric field points up and my dl points to the left. And then on the left side, my dl points downwards, but my electric field points upwards, so I get a negative dot product that has a magnitude of E times L. So this becomes the left side of Faraday's law, and I can recognize that this EL minus this EL are going to cancel and only leave me this term. Bella? How did I get this? This comes from this part of the loop, right? So when I'm integrating around the loop, I'm going all the way around. The first term over here comes from integrating the electric field times the length on the right side of the loop. And the second term comes from integrating the electric field, which points up, times the length, which points down, hence the negative sign on the left side of the loop. So we get on the left side of Faraday's law just this. The rate of change in the x direction of E times dx times L. Right? We had an L here and a dx there. On the right side, I've got the time rate of change of the magnetic flux. So there's some magnetic field pointing through this loop, and the area of the loop is just the area of this rectangle with width dx and height L. So here's my area, L times dx, and there's my magnetic field. So this gives me the flux, and I have to take the time derivative of that. But L and dx are just constants. So They're fixed in time, so I can pull them out of this time derivative, and I end up just taking the time derivative of the magnetic field on the right. And now I can see that the dx times L's cancel, which I'm hoping would happen because this is just an arbitrary loop that I drew, right? Whatever relationship I have between the electric and magnetic fields here should be independent of how I draw a loop in my diagram. And what I'm left with is this term on the left equaling minus this term on the right. So there's a relationship between the time rate of change of the magnetic field and the slope of the electric field, or the spatial rate of change that I get from Faraday's law. So this says if I have a changing magnetic field, there must be an electric field around it that varies, or vice versa. If I have a varying electric field in space, there must be a time-dependent magnetic field. Well, I can do something very similar with the magnetic field that was pointing in the z direction. I will assume that it's varying along x, but is pointing along z, as I drew it on the previous slide. And again, I'm going to approximate that changing magnetic field along x as a first-order Taylor series expansion of the magnetic field. So over here, at a point x plus dx, I'm going to have my original magnetic field that I had over here, plus a little bit. And the little bit depends on how fast the magnetic field is changing in the x direction, times how far over I go in the x direction. And so again, that's just a Taylor series expansion of b of x, and I've only kept the first term. So I'm going to apply Ampere's law to this. So recall Ampere's law with Maxwell's correction. Looked like this. B dot dl around a closed loop is equal to mu naught times I enclosed. And Maxwell's correction said we also have to include this displacement current, epsilon times the changing flux. So I'm going to consider Ampere's law, but I'm going to consider this in a vacuum. In a vacuum, there's no charges. There's nothing, right? There's no charges, so there's no flow of charges. So I is going to be equal to 0. And epsilon and mu are going to be epsilon naught and mu naught. They're the specific values for the permittivity of free space and the permeability of a vacuum. So what that does is it lets me simplify this a little bit. Like I can get rid of the I, and I can let epsilon and mu go to epsilon naught and mu naught. So if I want to consider another loop here that I'm going to integrate b dot dl around, and I again consider a loop of length L. So L is the length of the loop and dx is the width. And again, I'm going to integrate around that counterclockwise. Then when I do this b dot dl, I'm going to have this larger value of b on the right times L. Actually, b is pointing in the plus z direction, my L is pointing in the minus z direction. So I get a negative b at x plus dx times L. So I get negative the value of b at x plus dx times L. I get 0 when I go along the x direction on the loop because the magnetic field is pointing along z and I'm moving along x. So b dot dl is 0 for the ends of the loop. And when I go along the left side of the loop, my magnetic field points along z and I'm moving along z, so dl is along z. So b dot dl gives me a positive b times L along the left side of the loop. So this is the term for the left side of the loop. This is the term for the right side of the loop. And the top and the bottom of the loop don't contribute because the dot product is 0. And so this becomes the left side of Ampere's law. And once again, the LB's cancel out, and I'm just left with this term right here, which I'll hold on to for the moment. And now I'll look at the right side. On the right side, I'm able to get rid of the current term because I'm assuming I'm in vacuum where there's no matter, so there's no charges that can carry a current. And so I just have this mu times epsilon d phi dt. And I'm going to write mu and epsilon as mu naught and epsilon naught again because I'm in vacuum. And the electric flux is just the electric field times the area through this loop. So the area of the loop is L times dx, again, and the electric field I will write as E. So the time rate of change of the electric flux comes from the time rate of change of the electric field. L times dx is a constant, so I can pull that out front. And in this equation, then, I have an L dx on both sides. So again, that cancels. This analysis looks very similar to what I just did for Faraday's law. But when the L dx cancels, what I'm left with on the left is minus dB dx. And on the right, I've got this mu naught epsilon naught in this dE dt. So I have this relationship now between the rate at which the magnetic flux is changing in space and the rate at which the electric field is changing in time. There's a couple of constants in that relationship that I didn't have in the previous analysis. And for simplicity later on, I'm going to rewrite this. I'm going to solve for dE dt and just bring the mu epsilon to the denominator of the other side and write this like this. So I get this result when I consider Ampere's law. And I considered this result when I looked at Faraday's law. And now I'm going to combine those two results together. So from Ampere's law, the one that I just did, we had this result. And what I want to do is take the time derivative of both sides. So I'm going to take the time derivative of the left side, which gives me the time derivative of the time derivative of E. So the second time derivative of the electric field. On the right side, I'm going to take the time derivative of this whole right side. So I've just put that into the parentheses. But now, this minus 1 over mu epsilon naught, those are constants. So they're not changing in position or time. So I'm going to pull those outside of my derivative. And what I'm going to be left with is the derivative of b with respect to x and then with respect to t. But I can switch that order, and I can take the derivative of b with respect to t and then x if I want, and I'm going to do that. So on the left side, I have the second time derivative of e. On the right side, I have this constant pulled out, and now I've switched the order of differentiation. So first I'm going to take the time derivative, then I'm going to take the spatial derivative. And the reason I do that is because my result from Faraday's law tells me what the time derivative of the magnetic field is. So if I've got an expression for the time derivative of the magnetic field, I can just plug in minus dE dx right there. So I'm going to replace this term with minus dE dx. So when I do that, on the left side, nothing's changed. On the right side, I now have the spatial derivative dE dx. And if I bring this minus sign out here, it cancels that minus sign. And now I've got two spatial derivatives. So I'm left with this expression. So this is an expression that has a certain form that we call a wave equation. Because, as we'll see in a moment, the solutions for the electric field that satisfy this expression are traveling waves. So this will give us those electromagnetic traveling waves, or at least it will give us the electric traveling wave. Okay, so we'll show that traveling waves are a solution to this in a second. But what it is it's a second order differential equation. So solving it is not quite as simple as solving like an algebraic equation. In fact, there's an entire class on differential equations. So many of you either are taking it now or will take that for your engineering classes. But basically, the way you solve differential equations is you guess. You guess what the answer will be. So we're going to do that. But first, this was the electric field. I can do a very similar analysis to derive a wave equation for the magnetic field that has the same form. And it's going to be the same thing. I'm just going to start with the result from Faraday's law and then take the time derivative of both sides. And then I'm going to switch the order of differentiation to get this result, and then use the result of Ampere's law to replace this expression for the electric field with an expression for the magnetic field. And then when I simplify that, I get a relationship for the magnetic field that has the same wave equation form. So let's just look at the expression for the electric field. And if we can derive solutions to this second order differential equation, we'll have the same form of solutions for the magnetic field. Okay, so what we want is we want to guess what the electric field must look like. And because we can take the derivative with respect to x, and we get the same thing as when we take the derivative with respect to t, or when we take the second derivative, what we need is we need an expression where when we take the second derivative, we get something that's proportional to itself. That way, when we take the second derivative with respect to x, we get something proportional to the original function. When we take the second derivative with respect to t, we get something proportional to the original function. And if both sides are proportional to the same function, then they can be equal to each other. And this will be our constant of proportionality. We'll enforce that in a moment. But getting back to solving a differential equation, we just have to guess. So what form of a function, what type of function could the electric field have where when we take the second derivative, we get something proportional to the original function? Sine and cosine work. Any other ones? There's one more. Let's just look at cosine to start with. We've been dealing with cosine as our standard expression for sinusoidal oscillations. When we did AC circuits, we said cosine omega t was like the sinusoidal form of our alternating voltages and currents. So let's consider a cosine wave. What we want is an electric field that's varying in both space and time. Right? It has to be a function of x and t. We said for this example, it was going to be pointing along the y direction. So this is a vector that points along y. I guess I didn't write it as a vector. There we go. That points along y, so a y hat, that has some amplitude that I'll call E naught. That's the size of the field. But really the interesting part comes in the variation with respect to time and distance. So we said we're going to try a cosine function because that's a function when you take the second derivative, you get another cosine function. So the argument of this cosine function has to have a term that's proportional to x. So when we take the derivative with respect to x twice, the first time we'll get sine, and the second time we'll get another cosine. But it also has to have a term that depends on time, so that when we take the derivative with respect to time, we get the original function after taking two derivatives. And we know that for any sinusoidal function, we can have some initial phase, phi, that represents the phase of this, or the value of this this function, if it's not at its peak, at x equals 0 and t equals 0. So that's what phi is. It's just sort of this arbitrary starting point for my sinusoidal oscillation. And I've just written k as the factor in front of the x. For the moment, that doesn't mean anything. There's no physical meaning to k right now. It's just the factor in front of the x. We said the argument has to be proportional to x. So k is that constant of proportionality. And we're going to use omega as the factor in front of the time. And I put a minus sign in here, but that could be positive. And so this is a sinusoidal expression that's written as cosine. I could also write sine of the same type of argument. And really, these two expressions are the same, represent the same thing. It's just if you change phi by 90 degrees, you go from a cosine to a sine. So these both represent sinusoidal oscillations in space and time. There's one more function that when we take the second derivative of, we get the original function. Idea? Yeah, it's the exponential function. So we can say something like this. And this, remember when we were doing phasors, right? We said that we could represent a cosine function as the real part of a complex exponential. So if we write an exponential function like this, I've just made this k and this omega imaginary and factored out the I, the imaginary root there. And if I do that, then we can think of this as like a phasor and this as the real part of that. So we can solve this second order differential equation for a phasor or for the time-dependent function that comes from that phasor. So let's see, what happens if we take, let's work with the cosine function. If we take the derivative of that with respect to x, and I've got this here, I'll skip back to my computer. If we take this function written as a cosine, and we take the derivative with respect to x, what we're going to get is a sine function, actually minus sine, and then this k through the chain rule pops out front. So we get minus k times e naught sine of the original argument. And now if we take the x derivative again, the x derivative of sine kx minus omega t plus phi is going to be cosine kx minus omega t plus phi. And again, through the chain rule, we get this factor of k popping out front. So now we get a k squared. And so the second derivative of our function looks exactly like our original function. It's just got this factor of minus k squared. So it's still proportional to the original function with this constant of proportionality minus k squared. If I do the same thing with respect to time, when I take the time derivative of this, I'm going to get a minus omega popping out front. And because the derivative of cosine is minus sine, the negatives cancel. And now when I take the time derivative of this sinusoidal expression, the derivative of sine is cosine. And through the chain rule, I have a minus omega that pops out front. And so I get the second time derivative of my function is minus omega squared times my original function. So I have what I wanted. I have a function e naught cosine kx minus omega t plus phi that when I plug into this equation, on the left side I get something proportional to the original function. On the right side I get something proportional to the original function. And this equation can be satisfied if those constants of proportionality, k squared and omega squared, make this equation work out. So let's move those up. Here was on the left side what I get when I take the second derivative. I have minus k squared times the original function. On the right side, I have this epsilon naught mu naught from my original differential equation. And then when I take the second time derivative, I've got this minus omega squared times the original function. So because both sides are proportional to the original function, it means the cosine factor cancels out on both sides. And this simplifies to this relationship. The minus signs cancel, and k squared, which is what I'm left with on the left, when the e naughts cancel, the cosines cancel, and the minus signs cancel. The k squared on the left must equal epsilon naught mu naught omega squared on the right. So this trial solution that I proposed will satisfy the wave equation if, and only if, k squared, which was just this factor I put in front of the x in my guess as to what the electric field looked like, has this particular relationship to omega squared, which was the factor I plugged in front of the time. And so I can actually inscribe some meaning to what k and omega are if I recognize that what I've written here is a traveling wave, so it's varying in space and time, and if I wanted to observe this sinusoidal oscillation and how it's moving in time, I could pick a point on the wave. And a point on the wavefront, if you imagine like a surfer surfing along a wave and you wanted to calculate how fast the wave was moving by seeing how fast the surfer moved, you could say the surfer is at a certain height on the wave, and that means a certain phase, a certain argument to this cosine function. And as the wave moves, if we keep track of a point on the wave as it moves, that's equivalent to to requiring that this argument be constant. And as time increases, x has to increase as well to keep this argument the same. So this must be a wave that as time increases moves to the positive x direction. So this represents a wave moving in the positive x direction. If I had a positive sign here, then as time got bigger, x would have to get smaller, and that would be a wave propagating in the minus x direction. And so the phase of this cosine, kx minus omega t plus some starting phase, the rate at which that's changing in x is just k. The rate at which it's changing in time is just omega. And the speed of the wave, which I'll call c, is dx dt. And the rate at which it's changing in x is d phi dt. And in time is d phi, the dx is d phi dt, dt is d phi dx. And I know the rate at which it's changing in time is omega. The rate at which it's changing in x is k. So the speed of the wave is omega over k. So those factors that I plugged into my expression aren't just arbitrary values. They have some physical meaning. Their ratio is the speed of propagation. The other thing we can say about them is k tells me something about how far I need to go along in x before the oscillation repeats itself. That is, k will tell me something about the wavelength of the wave, whereas omega will tell me something about the period of the wave. So let's see that. If my expression looks like kx minus omega t plus phi, in order for that, if I plot that as a function of x, at some time t, it's this sinusoidal function, and as t advances, this whole waveform is going to move to the right. So we have what's called a traveling wave. I can ask, how far do I need to go in distance for the wave to repeat? That distance we call one wavelength, and we use the lowercase Greek letter lambda to represent a wavelength. And I can work that out from this expression, because if I say x increases by one wavelength, this repeats itself. So I get the same value. Let me move that down. So this waveform repeats itself when x increases by one wavelength. What that tells me is, if I expand this out, this plus lambda times k, I'll bring over here as an additional term. In order for this to equal this term, k lambda has to equal 2 pi, or an integer multiple of 2 pi, so that the sinusoidal function repeats itself. So after I move a distance lambda along x, the function has to repeat itself. So the argument changed by k times lambda. So I get that k lambda is 2 pi. So I can say either lambda is 2 pi over k, or I can say k is 2 pi over lambda. So if I have a wave that I want to represent mathematically, and I can look at it and see how long a wavelength is, I can use this relationship to figure out what k must be in this mathematical expression. Or vice versa. If I have a mathematical expression where I have some factor in front of the x term, I can work out what the wavelength must be by using the wavelength as 2 pi over that factor we call k. I can do something similar for omega, and I will just quote the results, that omega is 2 pi over the period of the wave, or the period is 2 pi over omega. So a period, as you'll recall from simple harmonic motion at the end of Physics 50, is the time it takes something to go through one full cycle. In this case, it's the time it takes the wave to go through one full cycle. As it's moving, if I looked at a point, let's say on this x-axis, it's going to go up and down and back. So as it goes up and down and back, that's one full period. Now, the distance that light travels in one period, the distance that it travels in a given time is the velocity. And if it travels one wavelength in one period, the velocity is lambda over t. And lambda is 2 pi over k. And t is 2 pi over omega. And so the velocity is omega over k. Which brings us back to what we had right here. Velocity is omega over k. Now, this constraint that I have when I evaluate my second order differential equation with my guess for what the electric field should look like, this needs to be satisfied in order for that guess to be a solution. So let's rearrange this a little bit to get omega over k. If I divide both sides by k, and then divide both sides by epsilon naught mu naught, and take the square root of both sides, I get this relationship. And omega over k has some meaning now. That's the speed at which the wave is propagating. And so if I'm in a vacuum, the speed of light in a vacuum is a physical constant that we give the letter c to, speed c. And evidently, that's 1 over the square root of epsilon naught mu naught, which is just really fascinating. The speed of light in a vacuum, if you think about how you would measure this, this is the fastest anything goes. Your traditional ways of measuring the speed of something, like taking a timer and a meter stick or something and having it travel a given distance and recording the time, that won't work with anything that's moving as fast as light. In fact, measuring something that moves this fast is extremely difficult. And there's a few exotic ways that this was done. Things like taking a pair of mountains and telescopes on either side of the mountain and a toothed wheel and spinning it really fast and sending light that gets modulated by that toothed wheel, reflecting it off of a mountain, coming back, trying to get it to pass through the next gap in the teeth to work out how fast it must be moving. Those were profoundly difficult experiments. But it turns out, from Maxwell's equations, the speed of light in a vacuum is 1 over the square root of epsilon naught mu naught. You can measure epsilon naught by measuring the capacitance of a parallel plate capacitor. You can measure mu naught by measuring the strength of a magnetic field produced by a current. You've done those things in lab. Right? I think you measured mu naught with a curve fit, didn't you? Yeah. Multiply those together, take the square root and invert it, and you get the speed of light without having to do this Herculean experiment of measuring something that's moving super fast. The other thing that's really interesting about this is this is the speed of light in vacuum. But we didn't say what our reference frame was. Normally in mechanics, when you measure the speed of something, it's always relative to something else. If I measure the speed of a falling bowling ball, it's relative to the ground. If I measure the speed of a person walking, it's relative to the ground. But if they're walking on a train that's moving, they're moving at one speed relative to the train and a different speed relative to the ground. We have this concept of relative motion. But this speed just comes from these two physical constants. And it doesn't say anything about what it's measured relative to. Einstein came along and said, that's because this is a constant. It doesn't matter. The speed of light is the same measured by a person who's stationary as well as a person who's moving near the speed of light. If I'm on a train that's moving near the speed of light and I shine a flashlight forwards, what happens to that light? You might think it just stays right in front of you, but if you're on the train, you actually see it advance forward at the speed of light. If you're off the train, you see it moving along at the same rate as the person. Those two things are incompatible, or seem incompatible. But Einstein came up with the resolution to that, and he said the reason they seem to be moving at different speeds for the two observers is because time is moving at a different speed for the two observers. This was time dilation and gives rise to the twin paradox. If you have a pair of twins, one goes off in a rocket ship traveling near the speed of light, travels for a few minutes and comes back. The observer who wasn't moving, that twin will have aged a full lifetime, whereas the one who was on the rocket ship will only be a few minutes older. So this is really wild stuff. If you're interested in this type of thing, Physics 122 is modern physics. It's a class that you can take that deals with these concepts, special relativity, quantum mechanics, things that we don't get to in the 50 series, but you now have enough background to do. And so if you're interested in that, you can actually take Physics 122 and get a physics minor. I think just that one course, together with the 50 series, gives you enough physics content to get a physics minor. Check with your academic advisor if that interests you, to be sure. But yeah, that's just sort of a picture of how this relates to more modern work. For our purposes, what we care about is light is now an electromagnetic wave, which itself was a huge revelation. Prior to 1865, there was great debate over what light was. Was it a flow of particles that somehow hits your eye? And Maxwell's equations show us that no, it's a fluctuation in the electric and magnetic field that propagate together as a wave. Okay, so this tells us light is an electromagnetic wave, and the speed of light is constant. Two profound realizations that come from these equations that were integrated together by Maxwell. Okay, so we worked out an expression for the electric field traveling as a wave. We're going to get a similar expression for the magnetic field. I'm not going to go through the derivation, but what we can do is we can basically use some dimensional analysis to see that the dimensions of E and B, in order to satisfy this equation, their relationships have to be related by a speed, right? Because we have a dx and a dt. So their relationship, if we first assume that they're proportional, a traveling electric wave and a traveling magnetic wave are proportional because the bigger the electric field, the stronger the magnetic field it can produce, and vice versa. And we relate them together with this constant of proportionality c, and then we evaluate these expressions. What we find again is this c is 1 over the square root of epsilon naught mu naught. That's the speed of light. So the ratio of the magnitude of the traveling electric field and the traveling magnetic field is the speed of light. So that comes up again. Okay, so other things that these equations show us that we didn't explicitly say, but fall out of this, is that electromagnetic waves are transverse waves, meaning the electric and magnetic fields are perpendicular to the direction of propagation. In our analysis, the electric field is pointing along y, the magnetic field is pointing along z, and the wave was propagating along x. That's what we call a transverse wave. So as opposed to like a longitudinal wave, sound is a longitudinal wave where the pressure of the air molecules pushing against their neighbor causes the air to vibrate, moving in a direction in which the wave propagates. Whereas electromagnetic waves cause oscillations perpendicular to the direction of propagation. The direction of propagation is given by the cross product of E and B. So E cross B we can find from the right-hand rule. In our analysis, if E was along y and B was along z, our thumb would point in the direction of the cross product, which is x. The magnitudes of E and B are proportional, and the electric wave and the magnetic wave will be in phase, which is the same thing as saying they're proportional. So when the electric field is getting bigger, the magnetic field is getting bigger. The electric and magnetic field are not in the same direction, though. They're perpendicular to each other, and they're perpendicular to the direction in which the energy is flowing. In a vacuum, electromagnetic waves travel at a constant speed that we call c. In a material, if we go back to our expression for c, it was 1 over the square root of epsilon naught mu naught. Epsilon naught was the permittivity of free space. Mu naught was the permeability of a vacuum. So you could probably guess what the speed of a light wave in a material would be. If we know epsilon for the material and mu for the material, we just plug those in. And if you remember, epsilon and mu were always greater than or equal to the values in vacuum, which means the speed in a material is always less than or equal to the speed of light in vacuum. One more. The waves are in the electric and magnetic field. They don't require some medium to propagate through. So you can have electromagnetic waves propagating through a vacuum. You cannot have sound propagate through a vacuum because sound is the collision of air molecules or whatever material the sound is transmitting through, bouncing off of each other. If you take away the material, you take away the ability of the wave to propagate. Not true for electromagnetic waves because you can have electric fields and magnetic fields in vacuum. They don't require matter, so they can propagate through a vacuum. So if we try to visualize this, here's an electromagnetic wave. Our electric field's pointing up at some point in time. Our magnetic field is pointing to the right, so the right-hand rule, E cross B, tells us the direction of propagation. We can identify a number of parameters. The period is the time it takes for the wave to go through one full cycle. So from now until now is one period. The wavelength is going to be the distance over which it takes the wave to repeat. So you could measure it from the peak of one wavefront to the peak of the next, or the trough of one to the trough of the next, or any 2 points that are repeated on the wave. The polarization of the wave describes the direction of the electric field. So if the electric field is pointing vertically, we would say the wave is vertically polarized. We could rotate this and have the wave polarized horizontally. And it's always the electric field that we use to describe the polarization. The magnetic field is always going to be perpendicular to that. Okay, so what I'd like you to do is have a chance to play with these parameters. So you can pull out your phones and scan this QR code, and that will bring up a little AR module here. You may need to turn your phone sideways in order to be able to dismiss that splash screen. But what we have in the bottom is our expression for the an electromagnetic wave. It's written in a slightly different form. K is written as 2 pi over lambda, and omega is written as 2 pi times the frequency. But what you see is like a little laser pointer over here and a wave propagating outwards. And we can change the parameters of this wave. Okay, so you can touch the top and move around to change the polarization to see what waves of different polarization would look like. Likewise, you can touch the amplitude slider and move it. So I'll make a larger amplitude wave. I can do the same thing for the frequency to see what effect a higher frequency or a lower frequency has on the expression. And as I'm changing any parameter, in the little white box, you can see mathematically which parameter it is that's changing. And then in the visual, you can see how that affects what you're seeing. The other thing that we can change is the speed of the wave. Of course, the speed is constant in a vacuum, but you can imagine what it would be like if it were faster or slower. So take a moment to play around with that. And as you do, the LAs and I are going to walk around, and we're going to try to test your understanding a little bit. So a couple things to think about. The yellow and the purple vectors represent the electric and magnetic fields. Which one is the electric field and which one is the magnetic field? Can you figure that out? So which color is the electric field? Hedia? It is the yellow one. How did you get that? Yep. That's right. So the electric field crossed with the magnetic field should give us the direction of propagation, and that only works if the yellow is the electric field. You can also check the polarization. If you adjust the polarization, the direction of the, well, it's not clear what axis we're measuring relative to, but it's the direction of the yellow that's being described in the box on the right. How about changing the speed? Did that affect the wavelength or the frequency or both? Yes? We can see by the equation that it's related to wavelength and frequency, but if we look at the image, is the wavelength changing? Let me slow it down. Let me speed it up. If we look at the visual, clearly the wavelength is changing. When it's traveling faster, we get a longer wavelength. When it's traveling slower, we get a shorter wavelength. Is the frequency changing? What can we look at to see if the frequency is changing? Try looking just at the point where the field is drawn at the initial output of the laser pointer. The rate at which it's oscillating up and down is the frequency. And what you should notice is that's actually not changing. So as I change the speed, the product of lambda times f is changing, but it's doing that by changing the wavelength, not by changing the frequency. Okay, so the last thing I would like you to do is to work in your with your neighbors to try to write down an expression for a traveling electromagnetic wave that has the following properties. It has an electric field amplitude of E naught, polarized along the x direction, propagating through vacuum along the z direction with a wavelength of lambda. So you're to come up with an expression for an electric field that has these properties. And here's a few hints for your expression. It should satisfy all 4 of these conditions. Okay, so let's see how we're doing. We should have a function that's varying in z and t. And how should we start this off? What's the first thing that I can write? Should be a vector pointing along x. So how do I represent that? Eric? Okay. It'd be the amplitude times, let's say, like an x unit vector. Okay? It should be a sinusoidal function of z and t. So I've written this as a function of z and t. And a sinusoidal function, let's use cosine. And because it's a function of z and t, there should be a term that's proportional to z and a term that's proportional to t. And then I can always have some starting phase. It should repeat itself when z increases by lambda. Okay, so whatever is in front of the z has to look like 2 pi over lambda, so that when z increases by lambda, this term increases by 2 pi. And it has an argument that stays the same when time increases by delta t and z increases by c delta t. So if time increases by delta t, and z increases by c delta t, I have to get the same argument. So what I have is some constant here, omega. And let's try a plus there. What I find is that as this term gets bigger, this term has to get smaller. So I should make one of these terms negative. Okay, now as t increases, z can also increase. And I know that when the time increases by delta t, the amount this should increase is 2 pi c delta t over lambda, which means omega must be 2 pi c over lambda. So putting all this together, I'm going to plug in for omega 2 pi c over lambda. And so a little bit messy, clean it up a bit. You should have something that looks like this. And let's just check. It's polarized in the x direction with an amplitude of E naught. So that's the biggest it gets. It's sinusoidal. It's varying along z and along t. As time increases, z increases in order to keep this argument constant. So this minus sign here is going to give me propagation in the positive z direction. And my value for k, that's the constant that comes in front of the space term, looks like 2 pi over lambda. The constant that comes in front of the time term is omega. That's 2 pi c over lambda. And 2 pi c over lambda, if I remember that c is lambda f from the AR module we did, 2 pi lambda f over lambda is 2 pi f, which is omega. The angular frequency is 2 pi, the linear frequency. So this has all those properties. Okay, so we'll wrap up here and pick up on this and deal much more with these expressions and propagating waves next week. But for now, have a good break, enjoy your Thanksgiving, and go Lions. Get that first win.